Let us begin by talking about vectors. So by the end of this little session here, again, you'll be introduced to vector components, and you'll be able to reduce a vector to x, y components, and you'll be able to add vectors by components, and you'll complain that why didn't you show this to me last year? I guarantee you that you'll say that. Please at least one person say that. I mean it. Does anyone remember this particular little GIF kind of thing from grade 11? Right? Vaguely? It was probably had a plane in the wind, and then it had a plane with no wind, a plane against the wind, and a plane with a sideways wind, right? And what was the deal with adding vectors last year? Like, how did we do it? You had to use a ruler and protractor, that's right, Joey, and you had to place them how, Peyton? Tip to tail, just like that, and then the resultant was from where you started to where you ended, right? And there was two ways to do it. You could either do it if they were a right triangle, well then you could use our very old Greek friend Pythagoras, and if it was not a right triangle, then you had to do it by scale drawing, which is what Joy was referring to, ruler and protractor. And there was always one or two people that, even though it wasn't a right triangle, tried to use Pythagoras and got written on their test, not a right triangle. And then they continued to do that to annoy me for some reason. Don't do that this year. Okay, so in our textbook, it is on page 79. So let's just grab that and have a quick peek there. Starting on page 79 is just sort of everything you learned last year about vectors, just a quick 5-minute little review, okay? Just to make sure that everyone's sort of up to speed kind of. In order to extend our study of motion to 2 dimensions, we first need to describe the process involved in manipulating vectors. The 2-dimensional plane's directions will be referred to as x and y. Positive y will be in the upward direction, and positive x will be to the right, just as you're already familiar with. Notice that the two directions are at 90 degrees to each other and are referred to as an orthogonal system. Math professors love that word, orthogonal. It just means 90 degrees. Yeah, orthogonal. Vectors are quantities that possess both magnitude and direction. Remember the supervillain? Vector? Getting crimes with both. Do you want to watch that? I'll see if I can find it.
You need to refresh it, I don't remember.
That's a load of hoo-ha, but since... Alright, so vectors are quantities that possess both magnitude and direction. The direction element of the vector is represented by an arrow, where the beginning of the arrow is termed the tail, and the end of the arrow is the head. To specify the angle of the vector, we use the compass system, north, south, east, and west, or the up, down, right, and left directions, along with an angle. It's best to keep the angle between 0 and 90 for future trigonometric calculations. Notice in figure 3.1 that the direction of the vector can be specified by 2 different angles. Of course, they are complementary or add up to 90, right? There it is. These angles are complementary and thus add up to 90 degrees. I was thinking ahead. So there's a couple examples there. A just shows a vector. B shows north 60 east is equivalent to east 30 north. And C there, what do you think the U and the L stand for? In part C. Up and left. Yeah, so it's up 30 degrees and then left. And then the bottom right one there, that would be west 60 south. Okay? There was also things like 60 degrees south of west that I showed you, right? And then we also have that bearing method that I like to use, which is actually what real people use in the real world. 0 there, 90, 180, and 270. And you have to be able to convert to that, right? Remember all that stuff? Brings back fond memories likely. Not so much. Flip the page. Adding vectors. Having learned to add from an early age, we're used to the meaning of the plus sign. For scalar quantities, there's no debate as to the final answer. 4 plus 3 always equals 7. But if we use vector quantities, the answer 7 is obtained only if the two vectors are collinear. There's another math professor word. What do you think collinear means? In the same line or same direction. Exactly. Otherwise, values anywhere from -1 to 7 are all possible depending on the angle between the vectors. In figure 3.2, you can see that when two vectors point in opposite directions, the total will be a minimum. The closer the two vectors are to being collinear, the closer their sum will be to the maximum value of 7. So if 4 and 3 are in the same line, then they end up being 7. If the 4 and then the 3 is kind of 45 degrees down to the right a little bit there, the resultant is 6.5, and if they're 90 degrees, it's 5, and if it's 3 is backwards a bit, then it's 2, and if it's the complete opposite direction, it's 1. Now consider the vector diagram D1 plus D2 illustrated in figure 3.3 as a guy going to school. The diagram represents a walk you took from home. You walked to your favorite place, perhaps school, perhaps not. Then you went over to a friend's house. The diagram of the walk is naturally represented by arrows. The process of your trip demonstrates the method of adding vectors. The head-to-tail connection of the vectors is how you interpret the plus sign in the vector addition equation. The vector addition shown in figure 3.4 are examples involving displacement and velocity. As long as you don't mix different types of variables in one diagram, in other words, you can't add velocity and displacement. They are apples and oranges. In the trip of figure 3.3, your net displacement is the vector drawn straight from the starting point to your final location. It is called the resultant vector, and I was so disappointed in Despicable 2 that the new villain wasn't named displacement, or no, a resultant. Resultant is what it should have been named. Not displacement, not stupid. Results are indicated in figure 3.4 by the vectors with hollow shots. In other words, those double line ones. Like the sum in algebra, the resultant is the result of addition, only this time we are adding vectors rather than numbers. Note that the resultant vector is specified by both the magnitude and direction. When you add distances traveled, the resultant vector is called total displacement. Blah, 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 blah. Let's skip to that paragraph right below figure 3.5. Okay, you need one of these. In summary, the plus sign in vector addition is an instruction to connect the vectors head to tail. When the vectors are collinear, you can simply add them. When the vectors are not collinear, you must construct a vector diagram or use trig. To calculate the result of two vectors, the trick for solving the triangle is straightforward. If your problem contains more than two vectors, which of course we will have to do, you will normally find it easier to use components. Using this method, you resolve each vector into components in the x and y direction, then add the magnitude of the components in each direction and solve the final right angle triangle. Its hypotenuse is the resultant vector. It's easy. It really is. Let's go to that sheet that you've got. In grade 11, we added two types of vectors. And I don't think you actually have this, right? No, you don't need this. It's written down. Vectors at right angles to each other, we use Pythagoras, right? Vectors not at right angles to each other, we use the scale drawing. Regardless, well, actually, that might actually be a right angle there, might it? Can't tell. Okay, but what would you do if you've got three vectors? Even if two of them were at right angles, the third one couldn't possibly, could it? So how are you going to do this? Well, in grade 11, remember doing the pirate treasure hunt? Maybe you did it when Mr. Sozek was here for me one day because I found a video when I was searching for something earlier. Yeah. Mr. Sozek was in, I wasn't here. Do you remember doing that, the pirate thing? Yeah. Okay. And you were supposed to get if Peyton and Jake were partners, Peyton's route should end up exactly where Jake's route ended up, right? And did that happen? Yeah. For some of you, it might have. Did every group have that? Probably not. And even if it was really close, was it ever perfect? I very, very rarely see people that are perfect. How come? Well, you make small little errors, right? Using components, there's no error other than rounding. Okay? You're going to get perfect answers. Okay? So in this case here, you would have had to go like that, and like that, and like that, and then there's your answer, right? And I think that's shown on your there, right? And if you all have the same picture, so you're all going to get the same answer. Okay, so let's do example 1 by component. I'm going to introduce you to the idea of components, and I'm going to show you how to add at the same time. So at the bottom there, we're going to find the x and y component of each vector. So it says 0.5 kilometers at north 20 east. Okay, so this is 0.5, and we're at north 20 east. So to find the x and y components, here's what you do. Complete this little triangle here. Oh, you don't have the triangle, do you? Yeah, you'll have to draw the whole thing, sorry. You could do it right there, I suppose, if you want. You could. Okay, so the x and y components, we're going to label this one D1. Unfortunately, use of components, and even pretty much all the way through grade 11 physics or grade 12 physics, the use of subscripts become more and more prevalent. So we're going to call this one here D1X, and I'm going to call this one D1Y. D1 for displacement 1, X for X component, Y for Y component. The X, of course, is left to right, and the Y is up and down. Okay? Now, using basic grade 9, I think, trigonometry, this is opposite. You know the hypotenuse How do I find this side? Using sine, cos, and tan. You can't, you only know this one side, Jake. You only know the one side and you know the angle, so you have to use trig. So is it sine, cos, or tan? This one. Opposite hypotenuse. Opposite sine. So we're going to say sine, let's just write it out full. If you want to skip this step, be my guest. Sine theta equals opposite over hypotenuse. So in this case here, sine of 20 is equal to opposite d1x all over the hypotenuse of 0.5. And I'm going to write it as d1x is equal to 0.5 sine 20. I would like to see you be able to get to starting your solution with that. You should be able to, by the end of this week, recognize this is opposite, that's sine, d1x is going to be 0.5 sine 20. You're going to know that it always works through these steps. Okay, so feel free to start your solution with that. So 0.5 sine 20. I should probably get my actual answer here. So 0.5 sine 20 is, I get 0.17. Okay. Well, by the way, there was a request to talk about sig figs, but I'm going to need a day or so to sort of get something together for you. I know, but Caitlin was telling me that, who was it, Caitlin, sorry? Riley, at ACC, you said? Red River. Their professor is... Okay, so I get an answer of 0.17. Now, I strongly recommend you do the y component right beside it. It doesn't matter whether you do x or y first. If you choose to do x first, do all the x's first. If you choose to do y first, do all the y's first. Doesn't really matter, but it's nice to have them in order. So, what's y going to be? Well, if this one is the sine, the opposite, this one's going to be the adjacent. So, can I skip those two steps, do you think? I'll write it out just for the first one. Cos theta is equal to adjacent over hypotenuse. So in this case here, cos 20 is going to equal the adjacent d1y all over 0.5. Or in other words, d1y is equal to 0.5 cos 20, which is 0.47. Have I lost anyone? We have to do one more thing before we move on here. We have to assign these directions. To the right is always positive, so my x is to the right, so my x has to be positive. If you want to include a positive sign there, you go right ahead. It doesn't really matter. The y is also positive. How come? Because it's up. So both of those are positive. If they were down or left, and you're going to see those, they would be negative. Will the x always be the sign? Will the x always be the sign? Like, will it always be d1x is equal to point whatever, sine whatever? Will it always be the sign? Why not? Okay, it could be in a different spot. Or you might have drawn it like this, actually. You're right. So if that's 20, then this one over here is going to be 70, right? And now the d1x is adjacent to the 70, right? So don't get that idea in your head that the x is always the sign. In fact, more often than not, the x is the cos. Just the way things are drawn. Regardless. Okay, so basically, I've introduced you to vector components, and I've reduced a vector to x to y components by doing what? Grade 9 math. Grade 9 math. Okay. Now I do it for this. Oh, there it is right there. I didn't even need to. Silly me. Okay. Now I'm going to do the next one. Now the next one is simple. D2 is in fact straight to the left, right? It's in fact 0.3 kilometers west. Okay, and I do this for a reason. The d2x is automatically minus 0.3. Does this d2 have any x and y components? It has only x. It has no y. The d2y is equal to 0. There's no up and down. Do you have to write in 0? It's probably a good idea just as a place keep. Okay, does that make sense? Yes? Okay, thank you.
Why is there 1 and 2? Is it just because of...
It's vector 1, vector 2, vector 3, and so on. Like vector 1, Peyton, was this one,
Okay, so...
right? D1, displacement 1, displacement 2. Yeah, we're doing that 3-vector addition question, right? Okay, so D3 is drawn like that. D3 is 0.8 kilometers at west 50 south. West 50 south. Right? So, and this is 0.8. The x is adjacent, so d3x is equal to minus 0.8 cos 50. Why is it minus 0.51? Why is the x minus? It's to the left. How important is that be negative? Is it one of those things like sometimes minus 9.8 you don't have to worry about? Or is this one of those ones where it absolutely positively must be minus? Or is it kind of eh? This is one of those ones where it's absolutely must be. It's very important. And the d3y is down, so it's going to be minus 0.8 sine 50. If the x is the cos, will the y be the sine? Will it always be that opposite thing? Yes, because if one is cos or one is adjacent, the other must be opposite, right? So yes, there'll always be a cos, there'll always be a sine. So we've now broken them down into components. We think the next step is to do. Add them all together. Exactly. Okay. And this is where it sort of becomes almost magical how easy it is. I'll pause for a second. The next step is to add all the x's together. Here it is here, right here. Okay? Rx, which stands for what? For me? Not prescription, no. Thanks, Peyton, yeah. Rx stands for x component of result. The x component of the result is the sum of all the individual x components. d1x plus d2x plus d3x, or 0.17 plus minus 0.3 plus minus 0.51, or minus 0.4. Is adding those 3 x components relatively easy? They're just numbers. You're just doing arithmetic there, right? Grade 7, integers. Next step, do what? Do the same thing for the y's. Which is where it says on your page, add all north, south, or y components, right? Add all y components. Ry is d1y plus d2y plus d3y. 0.47 plus 0 plus minus 0.61 to give yourself an Ry. What's the next step in the solution? On your sheet it says, use Pythagoras to find the resultant of the resultant components. So I drew it right here. My Rx, why is it to the left? Because my Rx is minus 0.64. Why is it down? Because my Ry is minus 0.14. And I automatically, why is it automatic? How come it has to be a 90-degree angle? Or does it? Will it always be 90 degrees there between the x and the y? Yes, it has to be. The x is left to right, and the y is always straight up and down. It must be 90 degrees. It will always be 90 degrees, which means you can always use the Greek guy. Yes, you can always use Pythagoras. So, and I really, 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 really want you to draw that picture. I really do. Is it absolutely necessary? Well, some would argue with me, but I think it's pretty darn important. Okay, just for visualizing. If I see that, if there's a mistake, if I see this, then that's more proof to me that you know what you're doing. You just made an arithmetic mistake along the way, and I can take that into consideration when trying to decide what to do word on mark for it. Okay? If you don't do that, then I got to do some more digging, and I may not be as generous. Okay, so I really encourage you to draw that picture, and I think it will help you solve it anyway. So, and then it's just a simple matter of doing this, right? R squared is rx squared plus ry squared. It looks way more complicated than it needs to be. I think you could follow this. You've all seen that type of stuff before, and you get an answer of 0.66. Is that easier than a ruler and a protractor? I don't know. Most kids say, yeah, I wish I'd seen that before. But remember, you're now a year older and you've got an extra year of math under your belt. And it makes a little bit more sense. I don't really think intro grade 11 can do that. I really don't. I could be wrong. You should feel special. Are we done? Generally, when the teacher says that and there's still something being covered up here, the answer is no. Why not? Angle, direction, right? Remember the supervillain? I need direction as well. Don't we all need a little direction in our life? Oh, you guys are quiet. Yeah. Is this one always going to be tangent? Yep. How come? Because you're always going to have the opposite and the adjacent. You do have the hypotenuse. You could actually use any of the three. You're right, Joe. I like to use, I don't know. I try not to use numbers that I've calculated in case I've made a mistake, but I guess I've calculated those. So. This is the resultant angle, Dallas. Yes. The resultant angle. So in this case here, you work through this and you get 12 degrees, so it's going to be west, 12 south. So in other words, when I add those three vectors together, and we're on the front of the page there, when I add 0.5 kilometers at north 20 east and 0.3 kilometers at west and 0.8 kilometers at west 50 south, my final answer, my final resultant is 0.66 at west 12 south. That's it. Like, it's not, that's it. I don't think there's...
Does it matter which side, like which trig function you use? Because I use sine and then...
You would get 12 degrees still?
Yeah.
Yeah, as long you have to use the hypotenuse, that's all right?
Yeah.
Yeah, yeah. Joy was mentioned that. No problem. It's funny.
Can you go back for a second?
Sure. I was excited about showing you the joke. So here's a chance for you to practice some of this and make sure you get it. The front page, all you do on the front page is break it into components. That's all you have to do. There's 5 of them there. Okay, all it says is break them down into vertical and horizontal components. You don't have to add them or anything. Or in fact, like in A there, we're talking displacement, and B, we're talking velocity, and so on, so you cannot add them. When you get to second page, BLM 2.2, it says add them using the component method. The first ones are just 2 vectors. The fourth one is a 3-way one. There's no way that they provided enough space there at the bottom. I find that amusing always, that they give less space to the hardest question. And then on the next page there are even more. They get more and more challenging as you go through. Okay, so pace yourself. If you're finding it easy, skip ahead. If that becomes too hard, scale back. I have a QR code for those of you with a smartphone. You can scan for that. Solution binder is there, and as far as I know, the solutions are online as well. Okay? So you have a solid half hour or more, half an hour to work on those, and I'll be happy to help you out with any of those.